Okay, here we go with the first part of our notes on liquids, solids, and solutions. This one we're going to focus on the liquids, and in particular the intermolecular forces that are at play in these different types of substances. The intermolecular forces is a pretty important unit. This will be showing up a lot in a lot of different questions in a lot of different formats. This is all really good stuff to know. So basically, as I'm sure you know, different states of matter is really comes down to the distance between the particles, right? In a gas, things are very, very spread apart, very low strength of intermolecular forces. Liquid, there's more attraction going on, so they're closer together. And then in a solid, you get a lot of attraction going on, so these guys are going to be much, much more closely packed. This is also going to regulate how they flow, viscosity, which is viscosity, and how they evaporate, things like that, boiling points, all those sorts of things. Because the solid and liquid states are much more closely packed, we refer to them as a condensed phase, and obviously the gas would not be. The state of a substance is that the state a substance is in at a particular temperature really depends on two different things: the kinetic energy of the particles and then the strength of the interactions between them. So if there's something that could be a liquid, right, and then you add some energy to it, you're increasing the kinetic energy such that it's able to break the attraction between the particles and become a gas. So the attractions between these guys, the intermolecular attractions are not nearly as strong as the intramolecular attractions between. This would be something like 400 kilojoules to break that bond versus 14 kilojoules to break this bond. So it's this is a much, much greater attraction, but this is a strong enough attraction that it can control the physical properties of a substance, like its boiling and melting point, its vapor pressure, viscosity, things like that. And so these intermolecular forces in general as a group are called van der Waals forces. So the different types of van der Waals forces that we'll be talking about are London dispersion forces, sometimes shortened to just dispersion forces, and dipole-dipole interactions, plus some other types of interactions like hydrogen bonding. Those will come a little bit later. So the London dispersion force is something that is created by an instantaneous in an induced dipole. So basically, if you've got an atom, right, generally these electrons want to be as far away from each other as possible. But occasionally, they could end up being close to each other, in which case this would then force those electrons to be farther away, and so you could end up with a partially positive end of this atom here and a partially positive end over here, and then you get some attraction. So the average dipole, so this is not a polar molecule, so on average it's 0, but at a given instant there could be an unequal distribution of electrons, so you get a temporary dipole, and then that can have an attraction to, or induce, and then create an attraction to a dipole next to it. So these forces are going to be present in all molecules, whether they're polar or nonpolar. So if they ever ask you, what forces are being held in whatever molecules, dispersion forces or London dispersion forces are always going to be there. This is because, or this increases, I should say, with polarizability. So the larger the electron cloud is, the easier it is to shift those electrons around and induce these instantaneous dipoles. So things that can affect the dispersion forces. So things that can affect the dispersion forces are the shape of the molecule. So if you've got a long, skinny molecule, like these guys that we're comparing, they're both C5H12, but they have different boiling points. This is 309 Kelvin, this is 287 Kelvin. Why is that? Well, this is a longer, skinny molecule, so more surface area, so you're going to have more dispersion forces going on, so greater attraction, which increases the boiling point. This one has less area for there to be dispersion forces connecting them, thus intermolecular forces, so it has a lower boiling point. Also, the dispersion forces tend to increase with increased molecular weight, so basically the larger atom, the electron clouds are larger and then are also easier to polarize. So if we're looking at, for example, your noble gases, as we move down the periodic table, their boiling points are increasing, and same thing with your halenes, right? Getting greater and greater boiling points because they're much, much larger, so they're getting increased intermolecular forces, so which which increases their boiling point, decreases the likelihood to separate those molecules. Dipole-dipole interactions, these are between things that have permanent dipoles, and so the positive end of one is going to be attracted to the negative end of the other, and vice versa. But these guys are really only important when the molecules are close together. So in a liquid, they're going to be less important than in a solid, but still important in a liquid, right? Like, this is one of the major things that's going on in water. So it's not that it's not important, it could just be less important. And the more polar the molecule, the higher its boiling point, right? So you've got a greater attraction. So in this case, we're looking at things that are roughly the same size, molecular weight 44, 46, 44, 41. Right? This was actually the smallest, but this has the largest boiling point. Well, why is that? Because this is the most polar, 3.9 dBis versus 0.1 dBis. So in this case, we can't use the size. They're basically the same size, so we look at polarity instead. So increasing the boiling point that way. So which is going to have a greater effect? Well, if you're looking at things that are a comparable size, then you can't really look at the dispersion forces. In this case, the dipole-dipole interactions are going to really what's going to dictate the boiling points of their physical properties. But if one molecule tends to be or is much larger than the other one, then you're more likely to have dispersion forces playing a bigger role in its physical properties. Which brings us to kind of an interesting trend here. So if you look at the non-polar series, these guys follow the expected trend. So we're looking at this guy right here. Right, so as you increase molecular weight, you got this increase in boiling point, which means you got increases in intermolecular forces. But the rest of these guys aren't doing that. You would expect these points should be all way down here, but instead they're way up high. So what's going on with these molecules? The smallest in the group actually have the highest boiling points. Well, that is caused by a special kind of dipole-dipole interactions called hydrogen bonding. So this happens when hydrogen is bound to nitrogen, oxygen, or fluorine. You get this unusually strong bond, right, called a hydrogen bond. And basically, this is because of the high electronegativity of nitrogen, oxygen, and fluorine, so they can pull those electrons pretty closely and create a stronger bond. And additionally, hydrogen, being that it only has that one electron, and you pull that one electron away, that nucleus is exposed, so then it creates an even stronger bond that way. So another type of force, this one is not a van der Waals force, but this is an ion-dipole interaction. So this is when you have something that does have a dipole, is partially positive and partially negative, could be attracted to something that's a permanent ion. So if we're looking at water, the partially positive here end is going to be attracted to the negative ion, negative chloride ion, and the opposite's true over here. The partially negative oxygen is being attracted to the positive sodium ion. So this is what's going to allow it to dissolve, which we'll talk about later. So basically, just to summarize these guys, you look at if ions are present or not. If there's no ions, then you look at if it's polar. If it's not polar, then it's only going to be dispersion forces. If it is polar, okay, is hydrogen bonded to nitrogen, oxygen, or fluorine? No, just dipole-dipole. Yes, then you're looking at hydrogen bonding, which is a special case of that. If ions are present, is it a polar molecule? Yes, you have ion dipole. If it's not, then it's straight up ionic bonding, which then again is the strongest of these intermolecular forces, really. So basically, like we've been saying, we talked about boiling point a lot, but the strength of these attractions really govern the properties of that substance, right? In addition to boiling point, another property we often talk about is viscosity. So this is resistance of a liquid to flow. It's related to the ease in which the molecules move past each other, and so it increases with stronger intermolecular forces and decreases with higher temperature. So think of something like honey, right? Honey, we would say, is a very viscous fluid. It resists flowing, but if you warm it up a little bit, then it pours a lot more easily, right? So you've got more kinetic energy in there, so you're more likely to break or to overcome some of those intermolecular forces and allow those molecules to move past each other, versus when it's colder, you don't have that ability, so it's a more viscous fluid. It doesn't flow as much. It's more sticky, literally and figuratively. Surface tension, another property that results from these intermolecular forces. So if you're looking at a water molecule in the center, it's balanced by forces all around it, right? all around that water molecule. Versus the top, there's no intermolecular forces up here, so that's what helps develop that skin that's on the surface of water that something like a water strider takes good advantage of, or even like the basilisk lizard that can run on water, or even like people, you can actually race snowmobiles on water. If you get going fast enough, you can just kind of keep moving across the water. So all that has to do with surface tension. So next we're going to talk a little bit about, we've been talking mostly about liquids so far. We'll talk a little bit about changing phases between different states, and so different types of energy that are required to make these changes. So red being an endothermic, so this is, you have to add energy to a substance. So if you want liquid to go to a gas, you have to add energy, obviously, right? Thinking about like boiling water. And then condensation is the opposite, right? That's an exothermic process. Energy is being released from the substance. So you can see energy levels going down. So what are some of these different phases in energies and things like that? So the heat of fusion, which is this red one here, is the energy required to change a solid at its melting point to a liquid. And as you probably guessed, that takes less energy than the heat of vaporization. That's the energy required to change a liquid to liquid at its boiling point to a gas. And then heat of sublimation is the energy required to take that solid directly to a gas, so to skip that altogether. So obviously that would take even more energy, and it depends greatly on the substance, right? Like mercury takes a lot more to get to that heat of sublimation over vaporization. You've probably seen diagrams like this for like the boiling of water, and when you are boiling water, or even taking something from ice, so starting at negative 25 C ice, and then you come up here to a liquid, and then a steam, it's not like this smooth curve like you might expect. Like the temperature doesn't change in a smooth curve. Well, why is that? And this is kind of cool. Like, for example, why do you get this flat line here when you're going between liquid and boiling? And that's because the heat being added isn't necessarily raised. It's going into pulling apart the molecules, and so it's being like absorbed by the water molecules to break them apart. So the temperature doesn't change during that phase change because you're breaking apart the molecules instead. And then vapor pressure, something we talked about in class a little bit, but this is basically saying this. So like we talked about with the gases, molecules in liquid do sometimes have enough energy to break free and become a gas at any given time or any given temperature. But obviously, as you increase the temperature, more of these molecules have enough energy to break free, which makes sense, right? This is kinetic molecular theory. So as more molecules escape the liquid, the pressure, their partial pressure they exert starts to increase, obviously, right? But eventually, you're going to reach this equilibrium point where the molecules evaporate, and that's at equilibrium with those same molecules then condensing and going back into the liquid. So that's that dynamic equilibrium. Dynamic because it's like they're always changing, but it's still in balance. Basically, every time something evaporates, something's going to condense. And so then that relates to boiling point. The boiling point of a substance is the temperature at which its vapor pressure equals atmospheric pressure. Right? So we think about water. Once you get more energy in there, you throw that equilibrium off. Now your vapor pressure is higher, and so more molecules are escaping as gases. They're overcoming atmospheric pressure, and so that's where the water starts to turn into a gas. And we talk about the normal boiling point is the temperature at which the vapor pressure is 760, or atmospheric pressure. And then we can also look at phase diagrams. You may have seen these in your intro chem. But basically, you can look at this and see under what conditions, any specific conditions, what state your substance would be in the places where where there's equilibrium between the different points. So first, you've got the liquid-vapor interface. So it starts at the triple point, where all three states are in equilibrium. And this ends at the critical point. And this is the point where basically you can't tell the difference between the liquid and the vapor. It just kind of becomes one, more or less, right? And then throughout here is that you're at equilibrium between vaporization and condensation. then this would be the boiling point, obviously, all along here, like we just talked about. The interface between the liquid and solid, this is the melting point. So anytime you're along this temperature at this given pressure, that's where you're starting to melt. And then the sublimation point is the point below the triple point where you can go directly from a solid to a gas. And then if you look at specifically at water, you have a pretty high critical temperature. So you do have pretty strong van der Waals forces because you've got the hydrogen bonding in water. So it actually is quite high temperature before you start to go to that critical point. And then as you increase the pressure at a certain temperature just below the melting point, the water goes right from a solid to a liquid. And that's it for that chapter.